types of dielectric. Now look at this table. Air is 1.0006. Well, for all practical purposes, we will take it as 1. Now, Pyrex glass, it has the highest value. Well, water has a very high value, but water is not a practical material to be used as a dielectric. So we will not be using water. Well, paper is a good dielectric, mica is a good dielectric, bakelite, all of them are commonly used to construct capacitors. Alright, let's move on. Now, I told you that the capacitance of a conductor, or now I'm going to say the capacitance of a capacitor. What's a capacitor? A capacitor is an arrangement of two conductors. Now, what are the factors on which the capacitance of a parallel plate capacitor depend on? Can you think about some of the factors on which the capacitance of a parallel plate capacitor depend on? Well, for one thing, you know that the capacitance does not depend on the amount of charge on the capacitor, neither would it depend on the potential of the capacitor. It only depends on the physical dimensions. That means, if I make a capacitor, tell me, if I make a capacitor with this kind of plates, another capacitor with this kind of plates, which will have a greater capacitance? Which of them will be able to store more charge? Well, obviously the one that has the larger area. So, capacitance of a capacitor can be increased by increasing the area of the plates. So, the first factor that determines the capacitance of a capacitor is the area A of the plates. The amount of charge that can be stored in a capacitor is directly proportional to its area. Well, here I have a parallel plate capacitor. The amount of charge that can be stored in a parallel plate capacitor is directly proportional to the area of the plates. We represent that by A. Now, what else does it depend on? Tell me, if I bring the plates closer together, if the plates are brought closer together, will it increase or decrease the capacitance? What do you think? Well, if the plates are brought closer together, the effect of the negative charges will be felt more on the positive charge. That means the potential of the charged conductor will be reduced if you bring the neutral conductor as close as possible. That means if the separation between the plates is small, the capacitance will be greater. So the separation D between the plates also is a determining factor on its capacitance. Capacitance of a capacitor is inversely proportional to the separation D between the plates. So we have now capacitance is directly proportional to the area of the plates and inversely proportional to the separation between the plates. What else it depends on? Well, obviously we have one more factor, the dielectric used between the capacitor plates. Is that right? Yes. Okay. The third factor is the dielectric constant kappa of the dielectric separating the two plates. Well, the capacitance is directly proportional to kappa. You use a material with higher dielectric constant, the capacitance will be higher. Now, can you combine all these and write an equation for capacitance of a parallel plate capacitor? Well, yes, we can. C is directly proportional to kappa it is directly proportional to area of the plates and inversely proportional to the plate separation. That means I can now use a constant. Look at the constant there. Are you familiar with this? Epsilon naught is the constant there. So the capacitance of a parallel plate capacitor equal to kappa epsilon naught A over D, where kappa is the dielectric constant of the dielectric between the plates, A is the area of the plates, and the D is the plate separation. Alright. And you know epsilon naught is the permittivity of free space. And what's its value? 8.85 times 10 to the negative 12 farad per meter. Okay, let's do a problem. An isolated spherical conductor of radius 10 centimeter is charged to 2 kilovolt. What is the capacitance of the sphere? What is the charge on the sphere? How does the capacitance change if the sphere is charged to 6 kilovolt? Well, you can actually answer these questions, all of them in one line, if you understand every concept we talked about so far. Now, what is the capacitance of the sphere? What is the equation for the capacitance of a spherical conductor? We just obtained about 10 minutes ago. Capacitance of a spherical conductor is 4 pi epsilon naught r, where r is the radius. The capacitance of a spherical conductor depends only on its radius. So the capacitance of a spherical conductor is 4 pi epsilon naught r, and we got all those values. The radius is 10 centimeter. All these are constant values. That will be 4 pi times epsilon naught, you know what that is, times the radius, and that is 1.1 times 10 to the, what's wrong in here? 10 to the negative 11, not positive 11. You will not get positive 11 if you do this. So the capacitance of our spherical conductor is 1.1 times 10 to the negative 11 farad. Can you imagine something that has as high a farad like this? This is a tremendously high value. Now, can you write this in terms of picofarad? 1.1 times 10 to the negative 11 is the same as, well, this is negative 11. It's the same as 1.1 times, well, it's the same as 11 times 10 to the negative 12, which is 11 picofarad. So the capacitance of the spherical conductor is 11 picofarad. Alright, what's the next one? What is the charge on the capacitor? Well, we know its capacitance. Its capacitance is 11 times 10 to the negative 12, or 1.1 times 10 to the negative 11 farad, and its potential is 2 kilovolt. Now, do you know a relation that exists between capacitance, potential, and the amount of charge? Well, C equal to Q over V. We know C, we know V, we can find Q. Alright, now from this relation C equal to Q over V, we can write Q equal to C times V. We will use this now hundreds of times as we go on. Q equal to C times V, and C is 11 picofarad, 11 times 10 to the negative 11, times V is 2 kilovolt, 2 times 10 to the power of 3 volts, and that will be 2.2 times 10 to the negative 8 coulomb. The amount of charge on that spherical conductor is 2.2 times 10 to the negative 8 coulomb. That is 22 nanocoulomb. Alright, let's do the C part. How does the capacitance change if the sphere is charged to 6 kilovolt? Well, what's the answer? Let me see if you get the right answer. Originally, we charged the conductor to 2 kilovolt, and then the capacitance was 11 picofarad. What will be the capacitance if you charge the conductor to 6 kilovolt? Did you get the answer? Well, what is the answer? There will be no change in the capacitance. Why? Because the capacitance does not depend on the potential. If you want to raise the potential to 6 kilovolt, that is 3 times the original, you've got to give the conductor 3 times the original charge. That means Q divided by V will not change. The capacitance of a conductor does not depend on the amount of charge, nor does it depend on the potential. The capacitance depends only on the physical dimensions of the conductor. Okay, we talked about that. Therefore, the ratio Q over V will remain a constant. Let's do another problem.